Hi everyone, welcome to this episode of Kipet Labs. In today's video we're going to do a little bit more calculation practice for titration. So going through a couple more practice questions that you have available in the booklet. Okay, so the first one that we're going to go through is question 14 on page 24 of the booklet. Okay, so in that question, we're talking about citric acid present in lemon juice. Okay, so we've got 25.0 mils of lemon juice, okay, that we're titrating with 0.55 mole, 0 mole per litre sodium hydroxide. And so we've got 25 ml samples of lemon juice were titrated with this, and we had an average titration volume of 29.50 mils. Okay, we're told that the molar mass of citric acid is 192.12 grams per mole. And so we're asked in this one, this is a multiple choice one, but there's no less work in this question, and we're asked for the concentration of citric acid in grams per litre. Okay, so that's what we're kind of working towards. All right, so what we have, we're told that it's a triprotic acid. That is, it has 3 protons that it's able to lose. Okay, so what I'm going to do, I'm going to call citric acid, I'm going to call it H3A. Okay, because we're going to do an equation, I'm going to call it H3A. So A represents the rest of the molecule. Okay, because I can't really be bothered doing the rest of it. But these represent the 3 protons that it's going to lose. Okay, that it's reacting with sodium hydroxide. We're going to get 3 sodiums for every 1 A, because this is A3 minus, and we're going to end up with water. Now, looking at balancing our equation, for every one of these, we're going to need 3 of these. Okay, we can also see 3 sodiums to 3 sodiums. We now also end up with 3 water molecules. Okay, so what we have here is we've got a 1 to 3 mole ratio that's going to factor in when we do the rest of our calculations. Okay, so our sodium hydroxide in this case is our known. So we start off with working out the moles of our known, the moles of our sodium hydroxide. Okay, so I'm just going to pivot a little bit here just to make it a bit easier to write. Okay, so the moles of sodium hydroxide are our concentration, 0.500 moles for every 1 litre, multiplied by the volume that we have in that. So 0.02950 litres. That is 29.5 mils expressed in litres. Okay, so we get a value of 0.016225 moles. Now, what we recognise from our equation here, that the number of moles of H3A, our citric acid, is equal to the number of moles of our sodium hydroxide multiplied by our mole ratio of 1 mole of H of citric acid for every 3 moles of sodium hydroxide. Okay, so we crunch those numbers, we do that calculation, and we get 5.41 plus some extra decimal places times 10 to the minus 3 moles. Okay, the fact that it's scientific notation is no bearing on our calculation. We keep going with it the same as we would any other number that's larger than that. Okay, so our concentration now, our molarity of our citric acid is moles divided by volume. So the moles that we've just calculated just now, and we're told that that number of moles was present in a 25 ml sample. Okay, so we get a value of 0.216 moles per litre. Okay, but the question is asking us to determine it in grams per litre. So we're going to need to use this value of molar mass. So we want our concentration of citric acid, concentration in grams per litre. So the units we want are grams per litre. So we have the value that we've got, which is 0.216 moles for every 1 litre. And we want to get grams over here and cancel out moles. So we're going to need to use our molar mass like this, so that moles cancel out. We're left with grams divided by litres, and so we get 41.6 grams per litre, which gives us the answer of B. So you can see that even though it was a multiple choice question, that there was just as much work here as for a 3 or 4 mark calculation question. You just have the benefit of having, 1 of 4 answers to choose from as your final answer. Okay, so you need to be prepared to do this much working for a multiple choice titration question like this. Okay, that there's every chance that they could give it to you like this. Okay, you need to be aware. Okay, let's move on to another question. Okay, so the question we're going to go with now is question 30 on page 33 of the booklet. So looking at a sample of dry ice, solid carbon dioxide that's contaminated, and using the process of titration to be able to assess the purity of this carbon dioxide. So the sample was reacted with sodium hydroxide with a known number of moles of sodium hydroxide according to the equation that we're given here. So 2 sodium hydroxides reacting with 1 carbon dioxide to make sodium carbonate and water. Okay, and then the amount that's left over was then reacted with hydrochloric acid, and then allowing us to work backwards from there to determine the percentage purity. Okay, so what we're going to do, okay, so we want to work out the moles of sodium hydroxide that were added at the start. I might see if I can just shift colours for a second, because my pen is starting to go a little bit weird. Okay, so we're told that we've got 50 mils of sodium hydroxide, that is 1.00 moles for every 1 litre, which gives us a value of 0.0500 moles. Okay, and so then that reacts with the sodium, with the carbon dioxide. We're left with a set amount of sodium hydroxide at the end. Okay, so what we need to now do is say, all right, well, in that titration at the end, how many moles of HCl did we add? Okay, so we add 0.02760 litres multiplied by 1 mole per litre, so it gives us the same number. Eagle-eyed viewers might have spotted that, just like we had up here. Okay, so that's how many moles that we added, which equals to the number of moles that reacted in that titration. So therefore, what we want to do is to use this, that's an N, work out how many moles of dry ice, sodium hydroxide reacted with the dry ice, okay, which is going to be the difference between these two values. The amount that we started with minus the excess amount is the amount that was used in the middle. Okay? And so, then if we look at this equation, that the moles of carbon dioxide that reacted in this in this reaction just up here is half the amount of sodium hydroxide. Okay, so the moles of sodium hydroxide multiplied by 1 mole of CO2 for every 2 moles sodium hydroxide. So it gives us 0.0112 moles. Okay, so now what it would be tempting to do is then say, all right, well, therefore, then that's in 0.616 grams and, like kind of work this out from there. But that's not how this question is supposed to flow. What we have to do is we have to say, all right, well, what's the percentage purity? How much of that 0.616 gram sample is actually carbon dioxide? So from here, we need to work out the mass of carbon dioxide that this would represent. So we're going to use our molar mass of carbon dioxide, 44.01 grams for every 1 mole. Okay, and so we get a value of 0.4929 grams of carbon dioxide plus a few decimal places. Okay, I'm just going to use the place over here. So now we want to work out the percentage purity. That is, how pure is that sample? So we want to do the mass that's actually carbon dioxide over the mass of the complete impure sample times 100%. We do that calculation and we end up with a value of 80%. Okay, so this titration question is a sort of thing that you do need to be prepared for, because they can ask questions that are quite novel. They don't have to ask just really kind of straightforward traditional titration questions. You need to be able to work with the data that you've got, to use some of the principles of knowns and unknowns to be able to do the calculations that you need to. Okay, I hope that gives you a little bit of extra insight. Thanks very much for watching. Bye for now.